introduction. Thanks for the invitation. And thanks for those of you who are joining. I definitely recognize some names, so I appreciate that. I'm going to share in sort of the maybe a non-traditional way, just so I can still see faces. And I just like to say that, especially with kind of a smaller group, we can keep things informal. If you have questions, comments, thoughts during the talk, please just go ahead and either interrupt or raise your hand. I'll try to monitor the chat as well, although that's always harder. So please feel free to just interrupt us. Okay, so the title is Online Non-Negative Matrix Factorization Applications, but I added a few slides about some recent work in CUR decompositions as well. So I'm kind of maybe under the more general theme of using matrix factorizations and tensor factorizations for interpretability. That will sort of be the theme throughout. So about half the talk is some new theoretical work, and then the rest will be a bunch of applications. And I can go through any of that, quickly or slowly, depending on how interested you all are. So the work that I'll be talking about is joint with a few folks. Here they are. So Dr. Han Liu, who's now a former postdoc of mine, now at University of Wisconsin. Laura Balzano, who's at Michigan. My PhD student, Chris Strohmeyer. Keaton Ham, who's actually not too far away from y'all, Texas Arlington. And then two current postdocs who will be leaving us this year, Longju Wang and Han-Chin Chai. In addition to those people, a lot of the applications that I'll show near the end is also joint work with my group and RU groups. So here's some nice photos. You can probably guess which ones prior to 2020 and which ones are post 2020. So it's been a couple of years in the making for a lot of these applications. So I just want to start kind of very general. I'm going to assume maybe no knowledge about what NMF is. So I'll just introduce briefly what non-negative matrix factorization is. So you can pretty much summarize it by this diagram, and I'll talk about the mathematical formulation in a moment. So say that we've got this data matrix, and just for convenience, I'll say that the rows correspond to users, perhaps, and the columns correspond to, say, variables. The goal will be to factor this into two non-negative components that will both be very low rank. So we'll imagine that the first factor will be, say, users by what I'll call topics. And I'll mention what topics mean in this context in a second. And then topics by variables. And so both of these will be low rank and non-negative. So you might ask, well, why is non-negativity even being mentioned here? So in NMF, because of the non-negativity constraint, you're asking that each column of the data matrix be represented by a non-negative linear combination of dictionary atoms, which would be the other variable components. And so thus these dictionary atoms are sort of these positive parts of the data. And so kind of the quintessential example, which goes back to the kind of famous paper by Lian Sung, which was published in Nature, where they take the data to be a bunch of human faces. And so each data column consists of a human face image, like you can see over here. And if you were to just do something, kind of typical, like PCA, for example, on the bottom here, you're learning components that indeed reconstruct the original image quite well, right? And so you see things like this. Of course, looking at this is meaningless to the human eye, right? This doesn't look like a piece of a face or anything like this. Nonetheless, the components do reconstruct the face quite well. However, if you require non-negativity, you get components like this, which maybe zoomed in doesn't look like very much, but if you can have really good eyes, you can look at this diagram over here where we've shown all of the different components, and you're actually picking out things like noses, ears, eyes, mouths, and things like this. And so you are really kind of learning things that are more interpretable to the human being. So they're still accurate in reconstructing the face. You can only lose maybe a little bit of accuracy because of the non-negativity constraint, but it gives you pieces that kind of make more sense. And so, again, this was popularized in this paper, and this is sort of the reason behind wanting non-negative factors. It's not for accuracy, it's simply for interpretability and explainability of the factors. So going back to kind of the general setup here, another way to interpret these topics. So if you have images, hopefully you look at the image and you can see that as a component of the image that makes sense. But in general data, this is how we'll kind of understand what the topics mean. So because, again, these are non-negative, I can look for large values. And one can put regularizers on these, as you can imagine, to promote sparsity and things like this. So there's just a few number of large values. But for now, we'll just assume it's kind of a straightforward implementation. So what I'm going to do is say I look at this topic here corresponding to the second column, and say I have a large entry in this area here. Then this would tell me that this user corresponding to this row has a large association with whatever this topic in the second column represents. Then you would ask, well, what does that column, what does that topic represent? You would go to the corresponding topic over here, find that corresponding row, and look for large values. And again, if you find a large value here, you would say, okay, this variable has a large association with this topic. And you're going to kind of piece these two things together until you sort of understand what's going on. So here's a more concrete example to really hopefully sink this in. So say we have users as our rows and movie ratings. So maybe each column corresponds to a movie and the entry corresponds to that user's rating of that movie. Then if we do this non-negative matrix factorization, we might look at, say, this topic here, which maybe would be a genre, for example. And I say, okay, this user has a large entry here. Let's go ahead and look at, see what this topic corresponds to. So I go ahead and look in this factor, and I look at that corresponding topic, and I see maybe 3 large entries corresponding to the movies Titanic, Love Actually, Sleepless in Seattle. Looking at these subjectively, I would then think, okay, maybe this topic corresponds to romantic films. And so maybe this user likes romantic films. And so you're kind of piecing these two things together. And this is how you, again, would be able to interpret these topics. From here, from these topics, you can then do prediction, classification, all sorts of other things. But you're using features that actually, again, kind of have this explainability. Okay, so mathematically, the goal of NMF, again, is to factorize the data matrix X, which I'll be writing as D by N, into 2 low-rank non-negative matrices, which we'll call W and H. W will be D by R, H will be R by N, so R will be the number of topics, and R is going to be a user-specified parameter, so I can choose how many topics I want to look for. And we're simply, without any regularization, we would just be looking at minimizing the objective function, which is just, say, the Frobenius norm of the error and the factorization. So just X minus the factorization W times H, with the restriction, of course, that W and H are non-negative. And so we'll kind of view this as a decomposition of the data into a dictionary encoding pair. So the dictionary here consists of the dictionary atoms, which kind of are the building blocks to the data set, and then the coding matrix, which sort of encodes how those building blocks are used. So the name of the talk had the word online in it. So we'll also be considering both a static version of NMF, which is just the previous problem, as well as an online variant, which considers data that's kind of streaming in over time or data that's being sampled over time, any sort of time series situation. So here, what we want to do is learn a factorization W and H that is best in expectation. So usually that means I'm putting some sort of stochastic model on the streaming data. And you can do many things with this. You can just simply learn what those factors are. We can use them for prediction, which I'll have lots of applications for down the road. This is sort of a schematic, which I'll explain in more detail in a moment. But the idea here is that the data matrices X1, X2, X3, and so on are changing over time. And we're learning W0 and H1, W1 and H2, and so on. So we're learning these factors over time. And at any point in time, I can just stop and reconstruct X by taking, say, W3 times H4 to reconstruct X4. But I can also kind of do this in sort of a sliding window where I learn W and H for all of the data that I have, but I kind of continue this window off into the future and I reconstruct into the future. And then I'll be calling that prediction. So that's a way of using prediction as well, is just use these factors and then do prediction into the future. I'll just mention here briefly that all of the work that I'll be talking about here can be extended to the tensor settings. As you can guess, things get tedious, it's harder to write down, and so on. A lot of the computations and proofs are non-trivial, but they are analogous. So everything will carry over into the tensor setting. But just for ease of notation and convenience, I'll just be using everything in the matrix case for this talk. Okay, so one of the first things I want to talk about is some convergence guarantees. So to minimize our kind of simple objective function x minus wh, and I'll be adding a regularizer here in a moment, but you can use something like block-Horn descent. So the typical method would be fix w, solve for h, fix h, solve for w, and so on, and minimize the error with respect to the other one that you did not fix. So that schematic can kind of be written up in this way, where x in this case is static, so it's just the same constant data set, data matrix, and we're fixing W0, solving for H0, fixing H0, solving for W1, and so on and so forth, and hoping that these iterates do actually converge to the minimizers here. And so if you kind of use this approach, but actually break things down iteration by iteration, you actually get an entry-wise update. And so this is a widely used multiplicative update, again, by the same two authors I mentioned previously. And breaking it down entry-wise actually just gives you a simple update that looks like this. And, okay, it takes a little bit of work to realize that this is really doing what the schematic shows above, but that's why I feel like this sort of method is really good for undergraduate research. So that's why I had many RU groups shown at the beginning who can kind of just dump into this, code it up very easily. The implementation is quite simple if we don't add any modifiers. And then you could do a whole bunch of applications right away. So what about convergence? So it is known that the error, this objective function, the Frobenius norm, is non-increasing with this multiplicative update scheme, but there's no guarantee to converge to a stationary point. Nonetheless, it's the most widely used in practice, of course. So we're going to go kind of more towards the online setting and talk about a stochastic model. So first, let's say that the data matrix X is randomly drawn from some sample space according to some known distribution pi, or fixed distribution pi. You need not actually know what pi is. Can we still learn the best dictionary factorization that describe the data X in some sort of law? And so this arises to the online non-negative matrix factorization problem, which concerns this sort of scheme here, which I already mentioned. So here the data is actually changing over time. So we're actually going to be applying a couple of models. One will be an IID model. This was already proven previously, where the data is just drawn identically and independent across time. But we're going to generalize this to a Markovian model, and I'll kind of explain why this is reasonable in a moment. So we're going to say that xt is an irreducible Markov chain on a sample space omega with some unique stationary measure pi. And then the goal of our ONMF problem will be to construct a sequence, W and H, of dictionary factors such that almost surely, sorry about this little thing down here, that almost surely this error, so x minus WH, converges as t increases to the best, so the minimum over all possible W and H pairs in expectation. So we're looking at the best W and H that explain X in expectation over the distribution that X is sampled from. So again, in the IAD case, this was already known. So this group of people here gave a good solution to this problem in the online setting, and they derived an almost sure convergence of an empirical loss. And this was for IID data matrices. And here, I won't go too much into the implementation. I just want to mention a couple of takeaways. So what they do is upon arrival of a new data point, xt, they are going to update H and W in this way. So we're solving two optimization instances. And the key kind of here is, okay, so I've added a regularizer over H. Again, that's to promote sparsity in the topics, just to help with explainability. But here, what we've also done is introduced a convex upper bounding surrogate for the actual empirical loss. And it's defined this way. Again, you don't have to stare about the details too much. I'll kind of highlight what the takeaway is here, which is that in the surrogate, we're actually recycling the previous found coding matrices, H1 through HG, and we're using them as approximate solutions to these subproblems. And so this allows you to solve only a single optimization for WT rather than multiple ones over and over. Something that you might worry about then is, well, then do we actually need to store all of the history of not only the data, which is used in this surrogate, but also the previously discovered factors, H1 through HT, right? We're talking about large scale applications. Having to store all of this history would be quite problematic. And so the good news is actually we can get around that. Again, a lot of detail here on the algorithm, but the two kind of key points here is these two aggregate matrices, AT and BT, can be computed iteratively, and they're reasonably sized. And this alleviates the need to actually store any of the history. So these are the only matrices that need to be stored over time. Just a single AT and a single BT in each iteration. So we only need to store these two, and that alleviates the need to store any sort of long history. So this is a very practical algorithm, and this is the algorithm that was shown to have some convergence guarantees for the IAD case. So this group of folks back in 2010 proved that if your data is IAD with common distribution pi, and you're learning your factors according to this above scheme, which is quite practical, then the following guarantees hold. So the empirical loss and the surrogate function that we're building do converge to the same constant almost surely. So that's a reasonable surrogate to use. The gradient converges to 0 almost surely, which of course gives you some piece of the convergence. And so this was a nice result, and the method works very well. We were starting to kind of relook at this in early 2020. And a lot of the applications we wanted to use were things like time series, COVID cases, for example, weather data, even sampling across networks and sampling large images. In all of these cases, unfortunately, the independence assumption is really not very practical. At least one would hope to believe that a COVID, case counts of COVID data, for example, from day to day are not independent. But being Markovian seemed much more reasonable to us. So not only do the actual time series that we're interested in studying have more of a Markovian property, but also even sampling, say, very large networks or very large images. To sample IID means you have to really balance across the network in a very challenging way if the network is very large. Whereas in a Markovian setting, you can do a random walk, which seems much more practical. So lots of reasons we wanted to see if we could extend this theory to the Markovian case. And so the good news is—
Can I ask?
Oh yeah, please.
So for the Markovian case, I understand that that is a better assumption, for example, in the COVID setting. But then how realistic is it to think of an invariant distribution for the COVID setting? At least at the moment, it seems like we are very far from equilibrium.
Yeah, for sure. This is one step towards reality. This is definitely not reality. It turns out, actually, I'll show some applications that we end up doing pretty well. But again, we're not changing the algorithm. We're just kind of generalizing the theory one step beyond. But certainly, I would be very interested in allowing other changes to the assumptions in order to get convergence. Absolutely, for sure.
Thank you.
Mm-hmm. Yeah, the good news is, at least for sampling, if we're designing a sampling scheme, we can make it Markovian. So in that case, it's quite realistic. But certainly for many applications of time series, this is just getting one step closer. I believe this is a much better improvement than independence. But yeah, as was pointed out, definitely still some improvements could be made. Okay, so in this setting, which I already mentioned, we have a Markovian data stream with a unique distribution pi. Again, same algorithm, we're not changing the algorithm at all. We just relax this assumption, and we get the same guarantees. So an expectation, the empirical loss and the surrogate loss converge to the same thing. In fact, they also converge to the same constant almost surely. And we also get that the gradient converges to 0. So same guarantees, just by relaxing this assumption. And I just want to say that because the team worked very hard on this, unfortunately, when you lose independence, most of the theory just completely vanishes. So this was definitely a non-trivial work. And I think, as was just asked, extending this even beyond these invariant assumptions would require a bit of work, but would be very interesting. So happy to chat more about that here. Any other questions on this before I move on?
Deanna, I had a couple of questions. Can you hear me?
Yeah.
Okay. The first question I wanted to ask was about the uniqueness of the decomposition. Seems to me that you don't have uniqueness because you can multiply by a diagonal matrix and it's inverse in the middle. So what kind of, which solution do you choose?
Which solution do I want, or which solution do I end up with?
Both.
Yeah,
so do you want, which solution would you prefer? And then does your algorithm tends to favor one of them?
Yeah, I'm not actually sure if anything has been proven about which solution you end up converging to. Probably that has to do a lot with initializations and things like this. So if you just initialize randomly and you apply this method, I'm not sure that there's any other guarantees other than what we're seeing here. What solution do I want? Typically for our applications, any solution which has reasonable accuracy, meaning X minus WH is not too large, and for which WH are non-negative and the topics are somewhat sparse, then we're happy because that gives us some explanation. So if I rerun it and I get something else, typically what we see in practice is the theme of the topics doesn't change very much. Sort of the overall takeaway is constant. Even though there are, small fluctuations in the values, kind of the genres, if you will, in that movie example are sort of still the same.
Okay.
Definitely, I'm sure you can construct counterexamples, but in the real applications that we've studied, we tend to see that.
Okay. And a second question, in any minimization algorithm, alternating minimization, so you have to solve a non-negative least squares at some point. Here you have a regularization terms, but let's forget about that. Which algorithm is used for the non-negative least squares?
Here we're still using the multiplicative update, the alternating method.
Oh, okay. Can you come back to that slide then very quickly?
This one?
Yes. So when you update the H and the W, so I'm just wondering how you keep the non-negativity. Is it obvious from here that everything is non-negative?
Yeah, it's actually guaranteed. You never leave. You don't have to do any projection or anything.
Okay.
If X is non-negative, which we assume it is, and you initialize reasonably, then yeah, these updates guarantee you maintain.
Yeah, because the. Okay, I see.
Yeah.
Thanks.
Yeah, so the method itself to derive is actually quite trivial. Okay, I just wanted to briefly mention some new work that we've done in CUR decompositions in the tensor case, and I'll have a few applications for this as well. So I wanted to kind of go back to square one. So let's remind ourselves what a CUR decomposition is in the matrix world. So say I have a D by D matrix A. I'm going to extract K columns of A and form a submatrix from those columns called C. Do the same thing for some rows of A, call that submatrix R. And take the intersection of those two columns and rows and call that submatrix U. So in this diagram here, C is red, R is blue, and U is the purple that's overlapped. The dimensions of these, so K will be smaller than D clearly, and so C will be D by K. R will be S by D, or S is the number of rows, and then U, the intersection, would then be S by K. Then the kind of classical theorem says if the rank of U, the intersection, is the same as the rank of the original matrix A, then you've sort of got enough to form the decomposition. So in that case, A can be factored as C times the pseudo-inverse of U times R. And so what we wanted to ask was, can this sort of CUR decomposition idea be generalized to multimodal data, so into the tensor setting? So some motivation, what one usually does when one asks that type of question, right, is just say, okay, well, matrix is a two-mode tensor, so can we just kind of view this in a more general way? So here's our decomposition, C times U inverse times R. Just writing this out by adding the identity, inside, and then viewing this as a mode-wise multiplication, you can actually see that indeed you can write this decomposition in a mode-wise multiplicative way, which sort of implies that one can maybe generalize this to more than 2 modes. So I'm just going to throw 2 theorems on here to get like a taste of what these look like. And then because that's a lot of notation, that's very heavy, which is typical in tensor work, of course, I'll have 2 pictures, which I think will make it a little clearer, but I'll just run through these anyway. So we derive 2 different types of CUR decompositions for tensors. This first one we're calling the Chidori CUR, which again, when I show the picture, that name will become clear. So we begin with a tensor A, which is d-dimensional in each mode, and just assume for simplicity that it also has rank R in each mode. Then just like we did in the CUR, we're going to be selecting sort of columns and rows. So select some indices, capital I sub I, for the rows, if you will, and then set this row tensor to be A restricted to those indices in each mode. And then do the same thing for the columns, where in this case, the columns are actually selected in a very specific way. So they're a function of the rows, and I'll show what this looks like in the diagram as well, and form that C matrix for each mode I. And then UI will be these C matrices restricted to the particular rows. So if this construction is done in this way, then you can say the following. That the rank of each U matrix is indeed R, the same as the rank of A in that mode. And you can form a CUR decomposition of A by doing a mode-wise multiplication of the row tensor R with these products, C1 times U1 inverse and so on. You also get that the rank of the row tensor R is the same as A. And you also have some rank statements for unfoldings of A. Again, if you haven't seen tensors, that's fine. We're just unfolding the tensor in a certain way to get a matrix and then asking what the rank of that unfolding is. If all of these hold, then you can also write A in this way. So something kind of very similar for a different type of CUR decomposition, which we call a fiber CUR. I'll just highlight the difference here is that these kind of column indices are no longer a function of the row indices. So you have a little bit more freedom in how you select these. And then we have sort of the same types of guarantees. So let me just skip over to the diagrams, which I think are much easier to interpret and sort of understand. So what I'm drawing here is a 3-mode tensor, which is this black outline. And we're going to kind of show the pieces of the CUR decomposition by these different colors. So that matrix C1 is obtained by taking this sort of red subtensor here and unfolding it along that first mode. And so here, these I kind of indices sets what corresponded to like the row indices are just these intervals that you can kind of see from each of these colors. And then the GIs were this kind of Kronecker product of those. So the C matrix is taken by unfolding this R, this red subtensor. C2 is taken by unfolding the green subtensor in mode 2. And then C3 is taken by unfolding the yellow subtensor in mode 3. And this dotted subtensor here shows you that R tensor. And so in this case, you can kind of see it in a nice way when these indices are nice intervals. So I think visually it's sort of clear how to build each CUR component, and then you get all of the guarantees. It actually does give you the proper decomposition. And so the reason that we named this Chidori is my postdoc was giving a talk and Dustin Mixon was in the audience, and he said, oh, this looks like a game called the Chidori. And so this is a picture of the piece in that game, and indeed it does look a lot like this. The fiber decomposition, which had kind of the more freedom, we were able to choose both the row and the column indices. Here it's kind of similar. I'm gonna make that thing go away. Okay. Yeah, here the lines that you see going in this direction correspond to the rows of C2, and the red within these correspond to the rows of U2. And they need not necessarily pass through this core subtensor R, so you have a bit more freedom in this case. and similar for C1 and C3, but we just didn't want to convolute the diagram. So again, lots of details here, and I'm happy to point you to the paper, but the kind of takeaway is that you can still do CUR decompositions in the tensor case. You have a little more choices in how you actually form them, but you can get similar guarantees to the matrix case. And I'll show some applications of why one might want to use CUR decompositions and so on in the remaining 15 minutes or so. So I want to just run through a bunch of applications now, and again, interrupt me if you have any questions on the previous talk. Okay, so the first big application that I've worked a lot in is in MyLime data. This is a patient focused, very large data project. It's hosted by Lyme-disease.org, which is the largest nonprofit for Lyme disease in the US. Lyme disease is a vector-borne disease typically transmitted by tick, insect, or blood-to-blood contact. And the symptoms often mimic those of other illnesses such as multiple sclerosis, ALS, Parkinson's, fibromyalgia. And it can become chronic, especially if not treated properly right away. The CDC estimates 300,000 new diagnoses each year, and there's plenty of evidence to suggest this is actually a very large underestimate. But this is believed to be higher than most cancers and HIV and many diseases that are very well studied. Unfortunately, Lyme disease is poorly understood, poorly funded, poorly diagnosed, and poorly treated, which seems prime for data-driven research. And so the CEO of Lyme-disease.org and I have been working very closely with this data. We've been able to do quite a bit of work just from this survey data. So it's a survey of hundreds of questions from about 18,000 patients. They need to have been diagnosed with Lyme disease by a practicing MD. And some of the questions, which I'm just going to focus on here, are symptom questions. So it's kind of the simplest subset of the questions. We just give the patient a list of symptoms that are common with the disease, and we ask them to say how strong their symptoms are in that category. And so I'm just going to kind of focus as an example on this rightmost graph here. And so the symptoms here are things like nerve pain, psychiatric issues, muscle aches, and so on. And we applied NMF and just asked for 5 topics. And I've kind of listed the 5 topics here as the columns, and I've just sorted the rows so it's a little bit easier to read. So large values correspond to dark oranges, and then very small values correspond to like pale yellow. And so I've just grouped them so you can kind of see how the topics look. So for example, this first topic has really only 4 large entries corresponding to nerve pain, psychiatric issues, muscle aches, and heart-related symptoms. The second topic here, and third and fourth, and so on. And so we presented this to the board of Lyme disease, consisting of mostly physicians, and a couple of things they got fairly excited about, one of which was actually this third topic here, this middle one, which corresponds to memory loss, twitching, sleep impairment, and cognitive impairment. So the fact that this revealed itself as its own topic coincides with some recent research in the Lyme community about different manifestations of the disease. It's now believed that the disease can manifest in a cardiac-focused way, a neurologic-focused way, musculoskeletal-focused way, and so on. This could be because of the person and their own physiology, or it could be because of co-infections, which happen very commonly with Lyme. And this topic here does seem to suggest that this is a neurologic manifestation. And so this kind of, again, supports this new conjecture about how the disease manifests. And also we can identify which patients are manifesting in this particular way, then we can design new treatment options that focus on that type of manifestation for those patients. So many things that could be done just by looking at this simple observation here. The other observation that they were quite excited about actually corresponded to kind of a neutral situation here, which is this bullseye rash symptom, which doesn't really appear in any topic. And for many, many decades, it was believed that if you had been bitten by a tick and had Lyme disease, then you would definitely present with a bullseye rash, so a rash that looks like a target. And physicians wouldn't give you treatment if you didn't present with the rash because it was believed that that was a very significant link. But actually in recent studies, it's looking more and more like only roughly 20 to 30% of people actually present with a bullseye rash, which means a very large group of patients are not getting treated adequately. And so it was really interesting to the physicians that this symptom sort of didn't correspond with any topics. So maybe it's not actually as useful and important as was previously believed. So many things that kind of just spark further discussion and more suggestions for clinical studies. In the image world, one can do a lot with NMF. If you want to build, say, a compression scheme, which is not what I'm promoting, that's not necessarily the best type of compression, but if you wanted a compression scheme for which the atoms that you're using to build the image actually have some sort of meaning, one can use NMF for this. This is actually online NMF, where we're doing a random walk across the image to get our samples. So we're sampling patches of the image. And the dictionary atoms that we use, that we learn, are shown here. So they do look like something visual. They look like kind of brush strokes or different blotches of color. And then this is the reconstruction here. And I believe this is 40% compression. So it does a fairly good job, even with interpretable topics. Maybe more interesting imaging applications are things like saliency or co-segmentation. So here we have a bunch of images that come from several classes. So some images contain a cow, a dog, a car, or a bicycle. So the image here is shown in this first row. And then we're using NMF in the bottom row here, or semi-supervised version of NMF, which I didn't talk much about, but allows for some user input for classification. In either case, we're able to predict which class each image falls into. But moreover, rather than just doing classification, we can also look into the algorithm and ask, well, why was this image classified the way that it was? Simply by using these features and looking at the topics that were used for that classification. So we do get some interpretability. So for example, in these cow images, the pixels in the image that were most highly corresponding to the cow label were, unsurprisingly, or I guess fortunately, corresponded to the actual animal, which might seem obvious, but this is a good thing, especially when we're thinking about bias and other things that are going into classification these days, to make sure that it's not the grass in the background or anything else like this. It's actually the animal itself that was corresponding to the classification. So for dogs, we typically see features like the snout being tied to that label. Cars, we tend to see things like tires and windshields being tied to the classification. Bicycles, again, kind of the wheels and the handlebars and so on. So we can use NMF for many different machine learning tasks. And the thing that I really want to promote and drive home is that we get interpretability as well. So we can actually look back and say, well, why was this thing labeled the way it was? Which I really believe is an important thing when we're moving into this frontier. We're starting to ask about the trustworthiness of AI. Here's an example, as I mentioned, using online NMF for prediction. And so this is COVID data. This was from early 2020. And we were looking at just case counts of confirmed cases, deaths, and recovered cases for the 6 countries that were first reporting data at the very beginning. What we're seeing here are the dictionary atoms that were learned, so the columns of the dictionary matrix. Nothing too much interesting going on here, except that in many of these atoms, you can see the orange curve is quite different than the others. And that's not surprising, since the orange curve corresponds to China, and in early 2020, they had much different behavior than these other 5 countries. But if we're going to use this for prediction, which, as I said, means that we're just learning the dictionary coding pairs over windows of time, and then studying that window sort of beyond where we end our current data and looking out into the future. And that's how we get our predicted value. So what we're showing here, this is for confirmed cases. These are, again, on the right, some examples of dictionary atoms. And what I'm showing here are the predicted values and the original true values. So the blue dots here are the actual case counts. And then the red were our predicted values. And so you see that in most cases, we actually do surprisingly well. For Korea, the US, Germany, Spain, and Italy, our predictions align with the actual data quite well. The one that we kind of struggled with was China here. And I think it's actually a really good example to point where we could improve. For example, here, China reported a very large spike in this case here. And because our data is learning these pairs over windows, in this case, the window was 6 days long, we're learning very local behavior. So our algorithm is going to believe that if we see a decrease and then a spike, we're going to expect to see that pattern again. And so we expect to see these kind of spikes appear. And it takes a while for the algorithm to realize that that's no longer happening. And then it sort of falls back. So what I would like to do going forward, and not just for COVID data, but there's many the data sets that have this type of property, is to incorporate a sort of global model with this more localized prediction. So in the COVID case, for example, I would like to incorporate an SIR model in addition to this sort of localized prediction. And then I think we could really benefit from both. Here we have also applied ONMF to EEG data. So this was a data set from UC Irvine. They have an EEG alcoholism data set where they tested patients that exhibited alcoholism and that did not. And the patients had 64 electrodes and they're measuring their EEG signal over time. And the goal of the data set was sort of to be able to classify the different neurologic behavior between the two classes of patients. And so here I'm just showing some examples of the dictionary items learned. And here we're showing things like correlation. So that's something, right, that's studied in EEG quite a bit, is how are each neuron, how are they firing together? So here we're just looking at a Pearson correlation of the raw EEG signal. And so you see kind of some very strong negative and positive correlations with some interesting patterns. If we just took the dictionary items that we learned and we took correlations in that space, then we get this set here, which might be a denoised version of the true Pearson correlation. I'm still working on kind of understanding what's happening here. Something even more interesting is the following. So not only do we want to look at the actual correlation of the signal itself, but we'd also like to see the correlation of the gradient of the signal, right? If neurons are firing together and increasing or decreasing together, then that is something that's important to study as well. And so here on the left, we're looking at just the raw data and its gradient and looking at the correlation there. And so you see a lot more kind of robust patterns emerging. If we do the same thing with the ONMF dictionary atoms, we get something similar. It's actually quite similar in this case. So here we were learning the dictionary atoms with the gradient and the raw data. But what I find very interesting is if we apply ONMF just to the raw data, we give it no gradient information whatsoever, but we allow for more topics, so kind of more robust dictionary atoms, then this is the Pearson correlation of just those dictionary atoms. And it looks strikingly similar to the previous two, even though this result here on the right was not given any gradient information whatsoever. It seems to still be recovering some sort of information that maybe is hidden in the raw data. And so this we found very interesting, and we're working with some folks in the medical school to kind of further understand what's happening. Kind of more neurologic data. Here is an example of a video. So this is functional MRI. We have a cortex of a mouse brain, and we're looking at regions of the brain that are highly active as a stimulus is being applied. This is over a 2-second interval. So here, kind of bright pink and yellow pixels correspond to high activity. And so we're applying ONMF here to this time series. And we're able to learn dictionary atoms in the space domain, which look like these 20 here. And then we also learn the corresponding coding features in the time domain, which look like this. So here, large values correspond to black and small values correspond to white. So what does one do with this? Well, one might look at interesting regions of the brain. For example, we picked out this picture here, which shows very focused areas of the brain. And we can say, okay, what time does this topic correspond to? And so we look over here in the time domain, and it ends up, I think, corresponding to this atom right here. And so you can see there's a very brief period of time where this region of the brain is highly active. And so this is an alternative way to kind of studying this type of experiment, rather than just looking at the video yourself and trying to kind of piece out some patterns together. This sort of really just throws it in your face. And so the medical team was able to kind of pick out the different regions that they were interested in and see when in time they were most correlated. So many fun applications. Here's, I won't spend too much time on this because we're running out of time. This is performance of the various CUR methods. I'll sort of show you a takeaway here. So here we're doing compression again for hyperspectral images, and sort of all of the methods do really well in terms of reconstruction and in terms of speed. It turns out that the fibers CUR is very fast, and the Todori CUR does the best in terms of SNR, but again, they're all sort of reasonable. So nice things one can do with the CUR methods in the Tensor case, so things like hyperspectral data. You can also do robust CUR, which is kind of analogous, if you're familiar, to robust PCA, which is a version of PCA that kind of can separate noise from the principal components. So this is used, for example, in detecting foreground and background and things like this. We can do the same sort of thing for CUR, and we can separate foreground and background in, say, video data. I think I'll stop there, and thank you so much for being here, and happy to take any more questions.